Our own eyes show us 4 stars which wander around Jupiter as does the moon around the Earth, while altogether trace out a grand revolution about the sun in the space of 12 years.
The Interplanetary Podcast. The exploration of space for the benefit of all humankind. Your hosts in England and Sweden, Matthew, Russell and Linn Boldt-Christmas.
Oh yeah,
Galileo, the one, the only.
Figaro, not Galileo, Galilei.
Yeah. The plural of Galileo is Galilei.
The past tense of William Shakespeare is would I was Shakespeare.
Oh, English.
No, I think I've done that joke before. The reason why I put that quote in, Linn, we actually speak about this at the final closing points of our interview that we did.
That's true.
About what it must be like to be the discoverer or something. This is from Galileo himself. I just love this paragraph that he wrote somewhere. And he says, I've observed 4 planets, neither known nor observed by any other astronomer for my time, which have their orbits around a certain bright star, Jupiter, one of those previously known like Venus or Mercury around the sun, and sometimes in front of it, sometimes behind it, though they never depart from it beyond certain limits, all of which facts were discovered and observed a few days ago by the help of a telescope devised by me. Through God's grace, first enlightening my mind.
He could have sounded really cocky there, but he was like, don't worry, it was God. I am the genius, yes, but I was led by the grace.
But how cool is that?
It's
the fact that he kind of acknowledges just how important a discovery it is and how bizarre it is that it's been done in the last few days by him and him alone, and no one else has seen it. I genuinely think it's got to be the most mind-blowing moment
I think it's amazing.
Of any human being.
Yeah, I think most people that do, actually, most humans full stop, but certainly most scientists have some kind of experience with this sort of like hyper-focused, mad maniac binge moment where it's like, I've been accidentally working for 16 hours and oh God, I haven't eaten this whole time. Wait, where am I? And like snapping out of it.
Only to discover that they've discovered the moons of Jupiter.
Yeah, like, wait, you look down at your notes like, wait, what did I say? What is this? Who wrote this? God?
So before we go any further, I must thank the 2 mega patrons who are Justin Roberts and Drew Wright. Thank you very much.
Thank you very much.
You are obviously legends.
Obviously.
I don't need to go on about what massive legends you are, but you know you're legends.
They already know.
And the rest of the gang will get a shout out at the end, as we do each month now. Who's our guest, Linn? Who's our guest?
So our guest today is a very special guest. I think I already waxed lyrical about her at the beginning of the interview. But her name is Bibiana Prinoth, and she is a PhD student at the University of Lund. And as regular listeners know, I may or may not have an affinity for my own research topic, exoplanets. Maybe I throw in some exoplanet stuff here and there. That's never happened before, right? So our interview with Bibiana is about a very special, particular type of exoplanet that you may or may not have heard of. Dun, dun, dun.
Oh, didn't we promise it? Didn't we?
Yeah. Never mind. I'll drop the suspense. But you guys already know what's coming.
No, don't.
Sorry. Okay,
don't. No. Let's keep the suspense going.
Yeah.
But I wanted to talk about the real Jupiter just for a bit.
The OG Jupiter, the namesake.
There were some really interesting studies that came out. Did you see the one that was in astronomy and astrophysics called Jupiter's inhomogeneous envelope?
No, I did not see that. Good words, though.
Obviously, the envelope is its atmosphere, like, those colours and stuff. And
science,
clouds.
yeah.
I'm sure science, all the science
All the
stuff.
sciencey stuff, yeah.
You could tell me what inhomogeneous means.
I'll let you tell the word, and then, yeah.
Yeah.
Inhomogeneous. I actually now I'm suddenly second guessing. Wait, that is how you say it, right?
Yeah, I think so.
Inhomogeneous is what my Swedish brain wants to say, because there's so many vowels.
I think that's okay as well.
Inhomogeneous. Yeah. Inhomogeneous, I think is the correct pronunciation.
Yeah.
It means not homogeneous. And it basically just means like not uniform, I guess. It depends on context. But in this case, I think it's talking about the uniformity of an atmosphere. I mean, when you think about atmospheres, you think of them as being basically the same around one planet, right? We're learning a lot about planetary atmospheres, both in the sort of science field and also here on the podcast. And we're going to be talking a lot about atmospheres in this episode.
Yeah. We're atmosphere fantastic.
Exactly.
That's the reason why I picked this little article. It came out on the 2nd of March. I saw it in Live Science.
Oh, cool.
And it had the brilliant title, Scientists Find Remains of Cannibalized Baby Planets in Jupiter's Cloud-Covered Belly.
Okay, that's so much cooler than the inhomogeneous envelope. That should have been the subtitle.
It should have been, shouldn't it, really?
They don't want to give it all away in the headline, I guess.
We talk about this in the interview, but obviously, as you know, when Jupiter was being made, originally was like a rocky core. As that core's got big enough, it's able to trap gas around it, and then it ends up with this massive gas envelope.
Exactly.
Right?
Yeah.
I'm right in saying that,
I
right?
think so.
Until the Juno spacecraft, there's been this one question of, did the core form out of little pebbles, like 1 centimeter size little rocks, or did it form out of planetesimals, like 1 kilometer sized baby planets?
Yeah.
Right. And it's like, which one of these is it? And you can kind of tell, because if it was if it's like clearing its orbit of planets, little planetesimals, then that could carry on going for as long as there's planetesimals in its orbit.
Yeah.
But it can't carry on going when there's little pebbles, because once the pebbles get big enough, it will get the gas envelope around it, and then the pebbles won't actually be able to penetrate the gas envelope and make the core grow bigger.
They're not sticky enough.
They're not sticky enough. Yeah. They're not sticky enough. They've used these computer models to kind of work out roughly how compact the core is. They reckon it's 7 Earth masses. Yeah. So it's a big old rocky core.
Big old rock.
It's a big old rocky core, and they're trying to work out things like the temperature and stuff like this of what it's going to be like, and these deep zonal flows and all kinds of things like that. But because of the Juno spacecraft, they've been able to measure the gravity, the way that the gravity changes as Juno goes around in its multiple orbits of Jupiter. It's on about 40 odd or something like that now. So they've been able to measure that quite accurately and discover that it's not very homogeneous. Yeah. In other words, it looks like it's the planetesimal model, because you'll have had all these rocks that wouldn't have had, as they smash together, they're of different masses and different densities is what I'm guessing. And therefore it's not as even as if it was all made up of pebbles.
That's really interesting. I haven't read this paper, but maybe I'm gonna shoehorn this into my thesis now, because that's a really interesting conclusion. So thanks, Matt, for helping with my with my homework, I was gonna say.
But that's really cool, isn't it?
Is,
so basically, a lot of the mass in the center of Jupiter had already formed as little planetesimals in its orbit. Yeah. Like I guess like it caught up with some of the Trojans.
This is something that we talk a little bit about in this podcast, about these formation processes about exoplanets. And one of my favorite sort of shortcuts when you're talking about tricky science subjects that we don't really know that much about yet is that you can always say that this is an ongoing research question, which is code for we don't know, but it sounds so like a really active kind of thing, like an active effort exists if you say that it's an ongoing research question. But yeah, really, that is the formation process is an ongoing research question in the sense that we don't fully know and understand it yet. And
yeah, but I love papers like this though, because it's like a little detective story, isn't it? That someone's thought, well, if it does it like this, then this is what we should see. And I guess it's a lot of it's computer models, lots of it's statistics. I mean, like you read this paper and it's just basically full of statistics.
Delicious.
It's but there's some other sort of really cool things in there as well, like the metals and all the sort of very dense stuff in the center isn't being mixed up in the atmosphere as much as they thought it would be. It's not being convected up. And so there's like loads of new mysteries that get chucked up as a result of
I don't know if this is true. This is just something I remember reading in a textbook years ago, so maybe it's not up to date. But apparently the core of sort of Jupiter and Saturn is apparently metallic hydrogen, which I think sounds so cool. And the idea is just that it's hydrogen that's so dense that it basically starts to act like a metallic conductor.
They have things like helium rain and stuff like that in there.
Oh, that's an album title.
But it's
Helium Rain.
Yeah, that is that Helium Rain.
For my non-existent dance.
It's a follow-up to Prince's Purple Rain.
A cover album where every cover is done with a helium voice.
Although Prince does sing in a high voice.
That's true. It's going to go extra.
So it's going to be very high.
Falsetto.
It's going to be very high.
Sorry, off track. Anyway.
I mean, it's definitely rocky, but that's the thing I think people probably don't think about is just how unbelievably dense it's going to be in the center of Jupiter. And in other words, one of the things about that is that as it crushes all these planetesimals together and all these pebbles, as it crushes them down under the force of gravity, that's when gravity is like there's so much gravity going on that you get loads of heat and more and more heat as it's crushing this stuff down.
Yeah.
And that causes all these convections in the atmosphere that you see things like the red, the giant red spot and all that, presumably. And so that's what makes the atmosphere of Jupiter so unbelievably exciting, because there's so much heat and energy.
It really doesn't get enough attention, in my opinion. I mean, I'm very excited about JUICE going to...
Oh my God, yeah, that's a big one, isn't it?
I feel like there's a correlation between people getting excited about particular planets after we go visit them. And I feel like we're approaching the Venus era and hopefully the Jupiter moon era and a couple like this.
The Jupiter's icy moons, I think, is really exciting. Maybe the Venus one's going to be super exciting as well.
I have high hopes.
Venus seems to have had a really raw deal. I mean,
really
it is like our sister planet after all.
We went in the 70s and our rovers didn't work.
Well, the Russians did. Well, I mean, the Russians kind of did.
We, humanity, went.
But as in, it doesn't seem to have been a priority for the Americans.
They were like, well, there's
Europeans,
definitely no oil here, so let's move on.
I suppose. I doubt it's that.
Well, no, I think my positive spin on it, my positive take would be that we realized back then how enormously challenging it would be to have a sort of long-term ongoing ground mission on the surface of Venus like we do with the Mars rovers. So it's kind of like Star Wars, where the special effects wasn't really available when they made the first three. And then like by the time the episodes 1 to 3 came, it was like, okay, well now we can go all out. And I feel like we've now matured as a human species, that we're emotionally ready to take on the challenge of Venus, which, I mean, if we try to go in the 80s, we just wouldn't be able to have made a mission then as useful as the one we'll be making sort of now in the coming years, I think. So in a way, it's okay. It is so hard to go there, and we had a little practice run on Mars. Now we're really going for the jugular.
It's actually mind-blowing, the technology that they send on things like the James Webb and the Juno spacecraft. The technology on that is mind-blowing. I mean, it's going at some points. It's going so fast that it's hitting that kind of relativistic speeds as it's whizzing in. And all that has to be taken into consideration with the electronics and everything. You go, oh my God, it's mind-blowing.
I get a little bit nauseous when I think about engineering too hard. It's a little bit scary.
The engineer. I think there's really brilliant examples about that collaboration between scientists and engineers, isn't it? Scientists want answers, and the engineers build something that will try and find those answers. And it is actually magical.
Yeah,
it is actually magical. Now, talking of magical, so I'm off to South America, to Karoo, to see the maiden launch of Ariane Vega C. I'm going to be commentating on the ESA channel.
How do you feel
about that? A bit nervous. So by the time this comes out, there'll be a proper launch date, but it's coming up early July. The thing that I've just seen that it's launching, because I'm doing obviously a little bit of research because I've got to kind of know
some
my
research.
stuff.
It's probably good too. You show up like, wait, what are we doing?
I keep saying to my friends, I've got some work to do. And say, well, it's not rocket science, and you go, oh wait,
actually.
So. Actually, damn, it actually is. But no, so it's launching one of the satellites along with a bunch of other sort of small satellites by various universities from Italy and France.
Like CubeSats?
Little CubeSats, little small satellites. But the major payload is this LARIS satellite.
Oh, of course.
In fact, it's LARIS 2. So the very first LARIS launched exactly 10.5 years ago on the maiden flight of Vega.
That's right. And now it's come full circle.
It's coming full circle. Now, the original LARIS is the densest known object orbiting the Earth.
Is that so?
Yeah.
Wow.
It's basically a great big ball. Yeah. There's no electronics on it. It's a completely passive object. Yeah. It's an enormous nickel tungsten alloy ball.
Yeah.
Right. And they launch it, and it weighs something like 380 kilograms. LARIS, the original one, did. It's launched into a very, very high orbit. Yeah. So it just goes spinning around. And the reason why it's super heavy is so it won't get pushed around by orbital forces.
Yeah.
All those like annoying things like
Those inconveniences.
solar radiation pressure.
Oh, yeah. That old chestnut.
So it won't get pushed around. It's covered in reflecting mirrors. These are reflecting mirrors. Apparently, they're off-the-shelf reflecting mirrors that are
Just
used
Tesco
for,
standards.
You know, Tesco standards. You can buy them down at Halfords. And but it's covered in these mirrors. And what they do in Italy is fire lasers at this ball as it spins around the Earth, and they're able to measure its distance within a centimeter.
Wow.
Which means that they can like track its orbit insanely accurately.
Yeah.
And what it's trying to do is actually work out the boundaries of general relativity. So it's looking at things like frame dragging and stuff like that, which is a kind of cornerstone of general relativity.
It's amazing.
How cool is that?
Is that what Laris 2 is? Is that a follow-up? Is it doing something similar?
So Laris 2 is almost identical. It's like what I couldn't find out was once this launches, it's going to be the densest object that we know of in orbit.
Do you know that tungsten in Swedish actually literally means heavy stone? Tung means heavy. And sten is stone. So it's just heavy stone.
It does sound like a Swedish word, doesn't it?
And you know what's really funny? Because the chemical symbol is just a W, which comes from wolfram, which is what it's called in Swedish. Totally different name. So the tungsten is only in the non-Swedish speaking part of the world.
So I'm assuming wolfram's got nothing to do with Wolfram Alpha, and the linguistics, the linguistics and search engine guy.
No, I think
it's not him, is it?
That would be very cool, actually. Or if there was,
it would be very.
Or if
cool
he was like
it'd be very old, I reckon.
the 10th generation, something like that. No, I think it's because the material itself has been known to humans for a long time, and I think. Tungsten was this old Swedish name for the mineral. I think, is it called scheelite? Which I think is like the ore that you would extract tungsten from. And wolfram, I think, is just something that other countries might use to refer to this kind of mineral. Or like wolframite is one as well. So I'm not 100% sure, but it's not called tungsten in Swedish. And the first time I learned that it was called that in English, I was like, oh, wait. No, what?
Yeah, wolfram apparently is from the German Wolfram, which means wolf soot. Or wolf cream.
That sounds incredibly haunted and cursed. So
maybe they thought it was something to do with wolves.
Yeah, werewolves maybe.
The actual, because in fact in Latin it's lupi spuma. That's that lupi is wolf, isn't it as well?
That's true, like lupus.
Yeah. So I wonder if it's werewolves' favorite metal.
There's
anyway,
a joke in there. There's a joke in there somewhere. We'll workshop it.
It's made out of a high density nickel alloy.
Yeah.
Laris 2. So and it's nearly 395 kilograms. So is that so it weighs more? But is it made of the same stuff?
Well, I guess if it's it must be quite small, right? If it's dense.
Oh, it's super small, but insanely heavy. And just won't get knocked around by heat pressure from the sun.
It's like, this is my orbit. Here I am. Frankly, an inspiration to all of us. We should all aim to be Laris in our own orbits.
So yes, that is the Italian Space Agency, the ASI, that are launching that. And it's going to be 6,000 kilometers in altitude, 70-degree inclination.
6,000?
Yeah, which will mean it will be in orbit forever.
That's too long, surely.
That's
very long.
Well, it'll be in orbit until the sun blows up into a red giant and then probably not.
Because for those who don't know, I mean, low Earth orbit is like a handful of hundreds of kilometers above the Earth. Yeah. So this is really pushing the boat. Or not pushing the boat because they won't get pushed around. I don't know.
Yeah, it's super high, but that means it won't be any kind of atmospheric drag at all either. So you don't have to take much of that into consideration. So they're able to make lots and lots of different measurements, not just about frame dragging, but lots of other measurements about about the shape of the Earth and the Earth's gravitational pull and all those kind of things. So it's an important mission, actually.
And you'll be there to see it launch.
And I'll be there to see it launch and to commentate on it. So that's going to be super, super exciting. In fact, exactly 4 years ago today, I was standing in Kourou looking at the launch tower for Vega, and they'd already fitted it out for Vega C.
Wow.
And I'd gone there to actually see the 120C booster be tested, but they never did. So that's how long it takes to develop these rockets. That was 4 years ago when they were testing the booster for this thing. So I'm really looking forward to that. It's going to be
sounds
totally
amazing.
Awesome.
So where can our listeners most easily find you when you're doing that?
I will definitely put it as a link on the website, and I would be tweeting about it.
Yeah.
I will tweet about my entire journey, but I guess it's on the ESA website or on the ESA YouTube channels and things like that. So just go to European Space Agency.
Yeah, you just find me.
Get there. or maybe Ariane Space or
any of the usual,
the Italian Space Agency. Yeah, all the usual suspects. But I'm really super excited.
I'm so excited for you.
And
I'm excited for me because I get to listen to you do it, and it's going to be amazing.
Yes. Yeah, exactly. It's going to be awesome. So that's one really exciting launch to look forward to. And did you see the picture that I've stuck in the notes of Jupiter and vortices, by the way, before we go to the interview?
Oh, yeah.
So there's a picture of plankton blooms in the ocean being swirled around by ocean currents. And then there's a picture from Juno of vortices on Jupiter, and they almost look identical.
It's crazy.
And so all the Juno data about vortices and how everything swirls around and how all those kind of mechanics of vortices works, all that data has been given to oceanographers to help them with their studies of the world's oceans.
Amazing. This is one of these things that I think one of the reasons to study space stuff in general is exactly this, because the thing is that the universe is like our sandbox where every kind of physics, chemistry, biology that you can imagine biology, asterisk there, but certainly physics and chemistry can happen. And we can study them in these extreme environments that we can't recreate in a lab on Earth. And this is exactly one of these kinds of examples where you actually get to learn something by looking beyond your planet to help you learn about your planet. Isn't that nice?
Yeah, it's genius. Well, look, it's funny, isn't it? Looking at another planet that's billions of miles away helps you understand your own planet that you're actually on.
Which is a great segue into the interview. What happens if you look at a very extreme type of exoplanet?
So here we go. Shall we just go straight to it?
Let's do it. I'm so excited.
I am very excited. Écoutez.
The Interplanetary podcast, putting the ace back into space.
So today we have the great honor to have the wonderful, beautiful, amazing Bibiana Prinoth.
Welcome to the show.
So Bibiana is not only a great scientist, but a good friend of mine. And she is a fellow PhD student here in Sweden, except she is at Lund University, which is down south. And Bibiana, like myself, studies exoplanetary atmospheres, but she has a much cooler research topic than I do because she's specializing on this particular subset of exoplanets. Not just any old exoplanet, but this particularly, I was going to say cool one. It's not cool, actually. It's the opposite of cool.
It's absolutely the opposite of cool.
And we promised this, didn't we? We actually promised this on the last podcast.
We did. Yeah, we did a teaser. Bibiana, I have to confess, before I even asked you, I was like, oh, I know what I'm going to do. I'm going to get Bibiana to get on here to talk about ultra-hot Jupiter.
It's like the Bob Geldof maneuver, that.
Yeah.
So you actually
can't disappoint
me
the fans
to listen to your podcast in advance and be like, wait, what? They're going to invite me? Okay,
yeah,
I see.
Exactly. Surprise.
Oopsie.
Yeah, so I think we've spoken to our listeners before about hot Jupiters because, when we're looking at planets outside of our solar system, we're obviously seeing planets of types that we don't even have in our solar system always. People know about small rocky planets like Earth and Mars and stuff, and then you have these big gas planets like Jupiters and Saturn. But the thing about exoplanets the thing about planets in other solar systems is that they don't always fit into one of these one or two categories, let's say. So hot Jupiters is a kind of exoplanet that we don't have in our solar system, which is a Jupiter-like planet, except it's much, much closer to the host star, which means it's hot. So, Bibiana, why don't you tell us what an ultra-hot Jupiter is then?
Oh, wow. So I guess if I start with that, I can get some people fighting over it, because I think there is no official definition for an ultra Jupiter that everyone would agree on. But we normally use it as being a hot Jupiter that has a temperature that is higher than 2000 Kelvin. At least that's sort of what I define it as. But I would say hot Jupiters in general are planets that are in orbits that are shorter than 10 days, so Earth days.
Wow.
So yeah, you basically try to limit it by that as a first measure, and then you go to, okay, now we look at the temperature, and if the temperature is expected, or the equilibrium temperature is expected to be higher than 2000 Kelvin, we actually call it an ultra-hot Jupiter. But yeah, people fight about it.
That's ridiculously hot. That's hotter than the surface of stars, right?
Yeah.
Colder stars. Yeah, solar type stars are like 5,000, 6,000, I guess.
Yeah,
but most stars are little kind of rubbishy, like red dwarfs.
Almost planets, basically. Little crap stars.
I bet that's...
Don't let the brown dwarf community
I
hear
bet that's
this.
hotter than Proxima Centauri or something like that.
No, I wouldn't say so. I know that there is one ultra Jupiter that I actually talked to my PhD colleague about this today. We would want to call it a ultra mega hot Jupiter, because it has a temperature of like 4,500 Kelvin, which is hotter than some stars. That is really the case. But I would say most of the planets that we know to date that go into this category of ultra hot Jupiters are more around, like, I would say maybe 3,000, 2,000 Kelvin, so really somewhere in between. So they're not quite as hot as stars, but definitely a lot hotter than we could ever imagine, and definitely not as comfortable as Earth.
Yeah, I've just looked up Proxima Centauri, and it's exactly 3,000 Kelvin. So it's not too far off, is it?
Well, I'm going to start by going off topic immediately just to get that out of the way. But I mean, because I'm just thinking now, when we look at Jupiter, and also in case our listeners don't know, we don't know that much about the interiors of the gas planets in our solar system, like Jupiter and Saturnus. Sorry, that's Swedish. Jupiter and Saturn and Neptune and Uranus. We don't know that much about their interior. We know a little bit from models and things like that, but it's very difficult to explore the surface of a gas giant or ice giant, because they don't really have a surface to land on in the same sense. But I'm wondering then, because I think what we think about those planets are that they have like ice cores, that even though they don't have a flat surface to stand on where there's a clear boundary where the surface starts and the atmosphere begins, but they do usually we think that it probably sort of gradiates into an ice core. But do we then know what's in the cores of hot Jupiters and ultra hot Jupiters?
I mean, you brought it very well to the point. We don't know anything, or not that much, about our own gas giants in our own solar system. So how are we even going to figure out stuff about planets that are light years away? So the problem with those things is that if you try to sort of limit what they are made of, you're sort of restricted to how do we even detect those planets. And then you can go into characterizing. So you need to know their mass, you need to know their radius. But that is really difficult to get, because we're observing, for example, from the ground, or we're also observing from space. But then there's just stuff happening all around. If you're observing from the ground, we have our own atmosphere that is sort of in the way. When we do this observation, so annoying, but we're so happy we have it, right? But on the other hand, it's like also, if you really try to characterize these kinds of planets, you will always hit a dead end very quickly, because, you can just not look into it. But I guess from a formation point of view, is one of the big questions that is still open. How did those planets even form? So how did they end up in these close-in orbits? I think we had a discussion recently, you and I, about how did those planets even form? Is it obvious that they had to form outside the so-called ice line, where you can form these icy cores? But what happens if they then move close into their host stars? This stuff's just melting. So I guess the hard part is, because we are observing them from here, from so far away, we end up just being able to see the very top layers of the atmosphere of these planets. So we have no idea what's inside.
That's true. And I mean, for those of our listeners who know about the transit method, when we look at exoplanets, when you see the planet that transits across the face of the star, and then that sort of backlights the planet enough that we can study it. When we're looking at the atmosphere that way, what Bibiana is saying is true. We're really only seeing the top of the atmosphere. You can't see that far down into it.
Well, I mean, when you're talking about observation here, how have you observed these ultra-hot Jupiters? What sort of signals are you getting? Presumably you're not seeing pictures of these things. You're just getting some form of signal.
We wish.
We wish we could.
Like Pokemon cards.
Yeah, that would be nice. Or just putting a camera out and just taking a picture with your iPhone would also be nice, right? No, so we are actually using different methods in order to study these planets. So we can either go and try to look at them in the sense of I want to figure out what their mass is, what their planet is. But if I really want to figure out what is in their atmosphere, I need to be super lucky and have them, as Linn said, going in front of the star as we observe them. And what we use are then instruments here on Earth, because we get them at so-called high resolution. So we're really, really able to distinguish from where the light comes, at what wavelength. And we really just observe them as they go in front of their host star, or as they sort of pass next to it in a sense. So not in so-called secondary eclipse when they're behind the star. So we get either the so-called transmission spectrum when the light passes through the atmosphere and parts of it are then blocked, or parts of the light are then blocked by the atmosphere, while when you have it on the side, you then have the emission, which is at a slightly different wavelength, given that the temperature is not as high as the temperature of the host star. And we use instruments like, for example, espresso on the Very Large Telescope. I have observed with espresso, but sadly only in designated visitor mode, meaning I had to sit at home via Zoom and I had someone else doing the actual work. And I was just there like, start it and then, end it. So they really did the work for me. But we were also sort of happy enough to get observations on La Palma, on the Canary Islands, where we could go and observe in person with the FIES spectrograph on the Nordic Optical Telescope. So we could actually sit in a control room and operate the telescope. So really from sitting there planning it, then pointing it towards the star when we knew the planet is going to move in front.
So I'm assuming you pick a what you hope is an ultra hot Jupiter. You point it at the star that you know it's going to transit in front of, and take readings that way.
So it's not all about luck. So we can actually calculate these things.
There's some thought that goes into these things. Thank you very much, man.
We're not just picking a random star. So there are a lot of things that have to go into it. So for example, you always have to think, is this star even bright enough that I'm going to be able to see it from Earth? But there are so many things that you have to take into consideration. But we mostly go for these targets, I would say, that fall in this sort of super puffy region. So we know, okay, they have a so-called inflated atmosphere, meaning that, yes, we call them...
puffy is the technical term, I may add, which I think is great. We literally say they're puffy.
Or super puffs, if you want to call it like that.
Or super puffs.
Yeah, so we sort of go for these planets where we know that their radius is a bit bigger. In the sense of, yes, I'm talking about an ultra hot Jupiter. So I would assume it has a radius of 1 Jupiter and it has a mass of 1 Jupiter mass, right? But they're actually inflated in the sense the mass is around 1 Jupiter mass, but the radius is then maybe 1.7 Jupiter masses. So they're actually a bit extended, meaning that it's easier to get this light passing through the atmosphere than actually also being able to see it.
Doesn't that lead to some form of like measurement bias that you're only kind of measuring?
Oh, absolutely. I was actually asked during the first talk I gave at a conference, why do you even care about ultra Jupiters? And I was a bit baffled by this question because I was like, oh yeah, it's my research topic.
You mean you don't?
You don't? But for me, one really big aspect is that this is really what we can do. So we are really biased towards these planets in the sense of it's not only their atmospheres being inflated, but it's also them transiting fairly often because of those short periods. So if you want to observe from Earth, you need to be able to point your telescope in during the night. You also need to be lucky that you have nice weather because we know we have clouds. We also know that some of these planets do have clouds. So it is really, we really have to sort of limit ourselves to the planets that we can observe. And now also with James Webb, for example, we will open the possibilities to also observe planets that are smaller and around smaller stars that are further away. But you still have to keep that in mind, that you have to observe probably multiple times in order to get enough signal out of this atmosphere. So it's not just all easy peasy observing those,
I was
atmospheres.
about to say, so it transit across, and obviously you're not actually seeing a black dot, are you? You're just essentially seeing a ridiculously small dimming of the host star, and then looking at that light and saying, what's missing now? And then working out what the atmosphere is made of that transiting object. Is that right? Is that my layman's version of it?
I think that's pretty much exactly what we do. So we really look at this while we know it is passing in front, and then we try to remove the star in the sense of we assume the star to be constant, which is also an assumption, of course. But we assume the star to be constant and try to remove the stellar light and say, okay, what's left is now the planet. It must be the planet because there's nothing else, right?
It's kind of like when you're learning algebra for the first time and you go from going that like 1 + 1 = something and you go to like 2 - something = 1.
Well, I mean,
do you know what I mean?
Here's a question for you. You're obviously looking for molecules in the atmosphere, or are you? And if so, surely at that temperature, most molecules have been ripped apart, haven't they?
That's a really good question. So I'm actually more interested in going for atoms or ions, because as you said, at these temperatures, molecules, that's going to be a difficult thing. So at these temperatures, you really have dissociation, you have ionization. So meaning that all these molecules get ripped apart and you have just their components left over. But you also have that some of these atoms get ionized through to this really heavy radiation coming from the host star. So lucky enough, there are also ways of searching for ions in a sense. And one thing that is very easy nowadays, or I would say pretty standard nowadays, is to search for iron in these atmospheres, iron and titanium.
But you still also get some fancy molecules, like metallic ones, for example.
Exactly.
And I mean, they're a little bit, metals tend to hold up better against extreme heats. Yes. What is it, titanium monoxide?
I thought astronomers called everything metal.
Yes, we do.
Yeah, my favorite metal is oxygen.
Yeah, so. I know.
But this is the thing. I think one of the reasons that I have a soft spot for hot Jupiters and ultra hot Jupiters is just because it is such a weird environment that we don't have an example of it in our solar system. The cool thing about astronomy in general is that it's the sandbox that can create crazy environments that we can't study in a lab on Earth. And so hot Jupiters is a great example of exploring what would happen under this very extreme circumstance.
I interrupted. What was it about these crazy actual metals? What was it? Titanium? Whatty?
Is it titanium monoxide?
Yeah.
Is one right?
I'm actually thinking, probably would be called titanium monoxide if you actually write it out, right? Because it has only one O, but we always say titanium oxide.
Is it titanium oxide? Yeah,
we go for titanium oxide. I was just thinking, oh wow, chemistry really passed me. So that has been quite some time.
It's like dihydrogen monoxide, right? It's
yeah, it's more like, what are you talking about? Yeah, no.
Yeah.
So titanium oxide has a pretty special role, supposedly, in ultra Jupiters, meaning that we can actually postulate, in a sense, what it is doing in these atmospheres. And this sort of, I guess it's a bit of teaser to my paper that I published in January this year. We detected titanium oxide on WASP 189b, which is an ultra-hot Jupiter. And titanium oxide is thought to be causing temperature inversions. And that is probably a bit a hard term to just throw out, but you can just imagine we also have that on Earth. So in our stratosphere, the temperature sort of is inverted. So the profile is inverted, meaning that if we go higher up, it actually doesn't get cooler, but it gets warmer. And this is caused, in our case, by ozone, while on ultra Jupiters, this is thought to be happening due to, for example, titanium oxide or vanadium oxide.
Now, how do you come to that conclusion? Is that something you observe or something you infer?
This is more something
philosophical question.
This is more something that you bring from theory, in a sense. There are quite a few papers that sort of start putting together these atmospheres, in a sense, or try to model them. as in trying to figure out what is the chemistry that is happening at these temperatures, what is the transfer that is happening, so how is energy transported from the lower regions of the atmosphere to the higher regions. And then they observe, okay, if we sort of add titanium oxide or vanadium oxide, we result in this temperature inversion in the end. So this is definitely something from theoretical point of view and not something that we could easily observe.
So you observed something, and then the experimenters come and say, yeah, well, if this was happening, then what you have observed is probably what's happening. So it fits the data, as it were.
Yeah, so I guess that's one of the big
battle.
points. Yeah, exactly. That's one of the big points that I find very fascinating, is that we try to sort of link theory and observations all the time, but we're not really able to predict properly what is happening or what we are going to observe. So yes, we have models, and then we assume something very drastically, like, for example, these atmospheres are isothermal, so there's just like one temperature. But on the other hand, we know that we are not able to completely reproduce what the observations tell us. And one of these examples is like we're observing ionized atoms, or ions, and we cannot really predict them from theory. So whenever we try to model them, they just get completely lost, and we're like, okay, where did they go? What has happened? And we just don't know the answer.
Yeah, it's why I think modeling is such a huge part of astronomy. Like, I mean, in all sciences, models, and I'm talking like computer simulations, are really useful. But I think in astronomy in particular, it's such an important bridge between theory and observation. Because if you have a theory that predicts a sort of behavior, and maybe your observations are not good enough because the thing that you're looking at is too faint or too far away, or your telescope's not good. And then by having a simulation that proves that, shows what the theoretical behavior should be, then you have something to compare your observation to. And then if it looks like it matches up pretty well with your model, then that is a stronger argument for interpreting your observation the way it is. I mean, think about if you're trying to, if you're looking at like a really blurry photograph and you're trying to figure out the face that you're looking at or something like that, it's a lot easier to figure out who you're looking at if there's like, well, here are 3 other faces. Which one does it look the most like? Because then you can be like, the color and whatever. So models are hugely important. Kids listening, if you want to be an astronomer, start programming.
Yeah, absolutely. I actually talked about that with my family, because I was like, you never gave me the chance to learn coding. And then my family was like, oh, wait a second, you studied at ETH in Zurich. And I was like, yeah, it was very theoretical. The studies were very theoretical. And now I basically end up coding every day. So I think if you want to become an astronomer, you definitely have to know how to code things up.
We are glorified programmers, basically.
Like, even if you're not a theory person, even if you're not working in theoretical work and trying to get atmospheres out there, or like trying to model these atmospheres, but actually observing them, you still need to have the skills then to reduce your data, for example, and being able to actually read something out of it. Yeah. So it's a very big part.
God, I can't think of a single branch of astronomy now that I'm thinking about it that doesn't use coding. Actually,
no, that's true.
It's a hugely important tool
and presumably so not just coding, but statistics as well. Presumably, there's a whole bunch of statistical kind of things that you have to know.
Long-time listeners may have noticed that there's a lot of things in space, which means that a lot of the time we have very large data sets and stuff like that. Now people are even talking about using machine learning for sort of astronomy applications. Say that you have 6 gazillion photos of light sources in the sky. Which ones are stars and which ones are galaxies? Like, you could go through them one by one, but if you can teach a machine to do it in like 0.5 seconds, then that's pretty good.
Yeah, one of the things about building observatories these days is the data is coming off so fast that you have to have water-cooled hard drives and stuff like that. It's like
exactly.
Yeah, absolutely. Statistics is definitely a very big part. Like, also, I think for me, it's very much learning by doing. So sometimes I'm like, okay, but how do I quantify what I actually detect now? So is this a strong detection? Is it just very weak? Is it tentative? Is it even there? So I'm really trying to sort of figure out ways that are sort of statistically sound in order to convince the science community that I'm actually detecting something. It's a very big part.
Does that make ultra hot Jupiters quite interesting? Because presumably they are extreme, they are big, they are hot. So so that some of these data points are actually going to be pretty unambiguous. Does that make them sort of slightly better to deal with?
That is absolutely the case. Yeah, in the sense of, I wouldn't say better to deal with, but I would definitely
not as bad.
Easier to deal with in the sort of sense that, yes, of course, you can still be unlucky and have bad weather. You can still be unlucky and have a volcano erupting on an island that you're supposed to be observing on. But
something that actually happened, by the way.
Yeah, it absolutely happened. It was nice to see a volcano in action, but it was definitely not so nice for the observation. I think that Ultra Jupiters are just more accessible, but they also offer, like, I'm not talking about them as like, they're the easy targets, you should really go for them because you get easy science out of it, right? No, I think the important part of behind Ultra Jupiters, they are so extreme and they're so different from everything that we know. So we are very much self-centered in a sense that we're always like, everything is like the solar system, right? So when we detected the first exoplanet around the sun-like star, we were like, but what is this weird thing? It's so much bigger than we actually thought. It is so much heavier than we actually thought. Oh, and wait a second, it must be so big or so heavy in a sense. Otherwise, it wouldn't have been detected in the first place. So it's very much about, this is absolutely not what we expected. And that's why people are curious and want to figure out more.
But presumably it's an extreme environment as well. So and extreme environments are normally good to study. They're normally interesting because they eke out certain things.
Yes, I also think, like, I always try to sort of compare it to Earth and then be like, okay, so if I try to compare it to Earth, what is the advantage of actually being able to observe an Ultra Jupiter? And I mentioned a few of like, it transits every now and then. Figure out if you have to observe Earth from somewhere else, you have to wait a year. And then if you're unlucky, it actually falls within a day and not a night. So you'll have to wait again. I guess the sort of other part that is very interesting is that the chemistry is completely different. So you don't have these really big molecules that we have that are making everything more difficult. And then you have to think about, okay, wait, what can happen to these things? Then also think of, if it's cooler, you will get clouds. We have them here on Earth. I'm not really happy with clouds and Ultra Jupiters because they will just block the light and nothing will come through. So we know that if you go to sort of hot Jupiters and then you look at their colder night sides, for example, or if you go to even cooler planets, that there are going to be clouds on them. And we have to make an attempt to model them on the one hand, but we also have to accept that they're going to be there and that there might be high altitude clouds that we are actually sadly observing in a sense. While on Ultra Jupiters, we mostly just neglect them because we know it's so hot that it's going to be really difficult for clouds. But this is very much like centered on what I'm working with, in the sense that we are mostly operating in the visible wavelength range. So I'm very limited to these ions that are very strong absorbers in these wavelength bands. While if you go then to other wavelength regions, you might have other components actually being stronger in absorbing. So if you really go to, for example, the infrared, which is also what James Webb is doing, or what Linn is doing. If you actually go to these infrared wavelengths, you have to think about whole different things. So just imagine one thing that is really strong absorbing in infrared is water. Where do we have water? We have water in our own atmosphere. So if we're observing from the ground, we have to think of actually removing the water first before we claim a detection. So we have to correct for that as well. So it's an easier target to go for something that we know is probably completely different from what we're actually used to.
Yeah, I mean, talking about that. So will James, once James Webb is up and running, is it?
Which is very soon.
It's imminent, isn't it? Will that get hot Jupiter? Will hot Jupiter get a bit of observation time? Is it worth it, or is there nothing to see in the in the eye of Webb, if you see what I mean?
I definitely see what you mean. So I know that at least for the first early data release programs, there are some observations of Ultra Jupiters planned that are basically also there to sort of confirm that it's working. the thing with James Webb is that I think is very interesting, given that it operates in the infrared and it's outside of our own atmosphere. We actually get the chance to look without having our own atmosphere in the way. So yes, ultra Jupiters are definitely a target. And one very important aspect that observing in space makes so much more interesting is that we're actually able to see these features coming in, and we don't have to so-called normalize it. So we don't have to sort of remove the star from it and be like, oh no, yeah, this star is in the way. So we sort of divide it out. So we only get relative abundances. While if we actually observe in space, we're going to be able to tell how much of something is in this atmosphere. And this is where James Webb is really, really coming in.
One of the reasons I'm so excited about James Webb, and as someone who does mainly ground astronomy, ground-based astronomy, is that you can actually use them sort of in tandem parallel, where
Exactly.
they support each other. Because the biggest difference between a space-based telescope and a ground-based telescope is, as Bibiana said, on the ground, okay, you have to wrestle with the atmosphere, which is annoying, it's in the way. But you have these huge, huge telescopes, and the mirror sizes on them are far, far bigger than even a huge space-based telescope like James Webb, where the light collection that you're getting, like the actual amount of photons that you are receiving, is much greater. And then, okay, on the other hand, your space-based telescope, sure, great, you don't have the atmosphere to deal with. The light comes straight in, but it's collecting a much smaller amount. So then the resolution, as Bibiana mentioned, is not as good. But then you can imagine if you take the big ground-based telescopes and a space-based telescope like James Webb, and you look at the same thing, then you have two pieces of data of the same thing, and you can kind of use the best of both worlds. Especially for some of these ground-based telescopes that we have do actually cover the same wavelengths that James Webb does. So you can get really, really, you're basically attacking the observation from two angles in that way.
I mean,
so it's very
for more
exciting
than
for
two
everyone.
angles in a sense, right?
Yeah.
Because I mean,
Yeah,
you're
exactly.
not only combining this sort of low resolution data from space from James Webb with the high resolution data on the ground, but you're also sort of combining different wavelength regions. So for
Yes.
example, you can always observe something in the visible while you then have James Webb observing in the infrared and get information from both parts. And also
Precisely.
sort of link it then back to what we talked about before, that you also will get some insight in how to model these atmospheres, given that you know more about them at some point.
Yeah. The chemistry in these atmospheres is so interesting. Something that's worth mentioning is that these ultra-hot Jupiters and hot Jupiters, when planets are very close to their host star, they tend to get tidally locked. So you get a permanent day side and a permanent night side. Unlike Earth, that spins around its own axis, you get this nice cycle of day, night, day, night. If you imagine that the planet is permanently, one side is always facing the star and one is always facing away, then you're going to get a cold side and a hot side, right? And so for a planet like Mercury, where this happens, then you have a hot side and a cold side, but there's no real atmosphere on Mercury. So you have like hundreds of degrees on one side and then minus whatever degrees on the other side. But when you have a gaseous planet like this, weather moves and atmospheres move, and it's like a fluid thing that goes on. So then you have these really interesting weather systems, and like what happens then at the perma sunset or perma sunrise on these planets. That's really cool.
Mercury is even more interesting if you think about it, because Mercury is not only tidally locked in the sense there is one hot side and one cold side, but it's actually in a resonance. So I think it's a 2 to 3 resonance.
I think so.
So yeah, I don't remember which way around. It either orbits in like two times while it turns 3 times, or the other way around. But you can imagine it like the moon on Earth. We're always facing or looking at the same side of the moon, because it's always facing the same side, because it's exactly turning at the same speed as it's orbiting, in a sense. And
precisely.
One cool thing you mentioned chemistry, but I think it's also worth mentioning dynamics in ultra-hot Jupiters. So because these planets are so close into the star and you have so much radiation coming from these stars, so we're talking about stars of temperatures with maybe like 8,000 Kelvin, so more than twice as hot as the planets they're that we're talking about. And they are just bombarding their planets with so much radiation. And then there comes this wind from the really backside that is heated up, that is permanently, as you said, a permanent day side. It just blows it around.
You've got the day side of this ultra hot Jupiter, and presumably that is where it's like your 2,000 to 3,000 Kelvin. It's like proper roasting hot,
way too hot.
But the other side's in shadow, right? So, but presumably it doesn't get that cold because you've got this ridiculous weather systems. I mean, there must be a lot of wind on that on a hot Jupiter, on an ultra hot Jupiter.
Yeah. So we're going back again to this sort of observational bias a bit that we have, right? Because we're looking at these upper layers of the atmosphere and we see that these winds sort of blow over, but there must also be some redistribution with like winds from the lower layers blowing back or something like that in order for the atmosphere to actually be maintained on both sides. I think the hard part with these observations is we're actually just probing the terminator region. So we're really, when they go in front, we're just looking at this very thin sort of annulus going around.
Where the sunset is?
Yeah, sort of, right? So we're sort of looking at this layer between super hot and super cold, if you want to make it super extreme. So whenever I have to draw it, I make one side bright red and the other dark blue in order to get people really excited about it. But it's more probably some sort of gradient that goes over these edges. And we are observing this light passing through this atmosphere in this terminator region, and we're also observing it sort of at different angles, if you want to say so. So because the planet is moving in front of the star, it sort of rotates ever so slightly while it goes in front of the star, resulting in different regions of the atmosphere being passed through while observing. And because the atmosphere is so inflated, you can actually try to disentangle where the light comes from and try to figure out, hey, is it from the morning terminator, as we call it, so the terminator that comes first, or from the evening terminator where it comes second or afterwards. And
the evening terminator that says, I'll be back.
Yeah, exactly. And then you have these two terminators that contribute in a different... They have these two terminators contributing in a different way. And yeah, you can sort of see these differences also in chemistry on these two edges.
And presumably that's when it first starts transiting. It could be its evening terminator, and when it's leaving, it could be its morning terminator.
It's exactly the other way around.
It's the other way around,
actually.
Isn't it?
Yeah.
Damn it.
So the thing that goes first is in the morning.
I was going to go that way
round.
round. I thought it's bound to be the other way round. So I'll say it the counterintuitive way.
I must admit, I find morning and evening terminator really stupid as a naming convention. I would actually go for leading and trailing terminator because it just makes more sense.
That
because
makes
we're
more
not talking
sense,
about morning and evening on these planets anyways. Who defines a morning and an evening on a planet that is permanently hot?
What are the time zones?
Exactly. What are the time zones, right? Yeah. That's not going to time zones. They are bad.
Yeah. But I mean, it's so crazy because, I mean, take a stupid, boring planet like Earth. And I mean, I've said this before and I'll say it again. Imagine that you're an alien looking at Earth and you're like, okay, rocky planet, has some water oceans, like 15 degrees average. Okay. Then you look at Earth for real and it's like we have the Sahara Desert and we have Brazilian rainforest and we have the French Riviera and we have the North and South Pole. Like we have so many different, first of all, climates, then seasons, and then like local weather patterns. It can be raining here and not 5 kilometers away. Like weather is so complicated and there are so many things that influence it and shape it and form it. And, you know, we can't even predict the weather on our own planet more than
including life.
A week or so.
I mean, life itself has a profound effect on the weather. So, I mean, yeah. But presumably when you get to something that's like mega extreme, you're cutting off those kind of subtle...
Do you think the weather on hot Jupiters, are they more or less complicated than like a sort of Earth, like with a, you know, dynamic oceans and sequestering into rocks and stuff like that? I don't know. Are they more or less complicated, do you think?
You're giving me the hard questions today.
I'm so sorry.
I love that question because in my mind,
I don't know the answer. I don't know the answer.
I'm on the edge of my chair thinking, yeah, I can't work this one out. Is it going to be more complicated or less complicated?
I would say we have to expect that it's probably going to be different in any possible way that we could have ever imagined.
Okay.
Who would we
Nice
be
diplomatic
to
answer.
Yeah, I mean, I'm Swiss, right? I'm neutral. I'm trying to be
very neutral.
I think that we have to stop thinking about us as the prime example of everything.
Yeah.
Be it, just think back in history when we thought that we are the center of the universe or the center of the solar system, not even universe, solar system. I think that we have to sort of be open-minded and go for, okay, this is probably nothing that we could ever imagine that is happening on these planets. And yes, we're trying to model it. Yes, we're trying to observe it and understand what we're seeing. But most likely we're going to be here in a few years, whatever amount you want to put in there, and be completely like impressed and out of our minds with what we're going to observe and going to see. Just imagine being able to travel to something different in a sense, or like taking a spaceship and going somewhere, travel wherever you want and look at it close up.
It may be the same ballpark, but it's not the same sport.
Here's a question for you. I mean, presumably these ultra hot Jupiters are extremely close to their parent stars. Like that, like they I've read somewhere that they orbit every 2 or 3 days, some of them, like crazy close. Now that's close enough, isn't it, where in the region that we don't even understand our own star about why it's so hot there. You know, we like one of the primary space missions is to try and work out why the corona is so hot. Is this something that once you get data from that spacecraft, that it feeds into what you're doing? Is this one of those things where you're looking cross-discipline across lots and lots of different data points to try and make sense of what's happening at your end?
I was actually at a conference in Las Vegas in the beginning of May, where it was actually an exoplanet conference, but we actually had some speakers that were talking about stars and that were like, hey, you cannot just forget about your stars. We're like, yeah, but we just ignore them. We just remove them and we don't care
boring.
about them.
It's like forgetting about Dre.
Definitely it's absolutely something like that. Like we always tend to forget that the star might be also behaving weirdly differently than we expect it to do. And I guess we have to start opening our minds, actually taking into account what we learned from the sun. But then we also see that, of course, the sun is probably not the best example for the stars we are looking at when we're observing these planets. So some of the most well-known ones, they're orbiting so-called A stars, which are stars that are a lot hotter. So I talked about like 8,000 Kelvin before. Some of them are 10,000 Kelvin hot. So nearly twice as much as the sun. And then you sort of end up with, okay, but how do these stars compare to the sun? And then you get down a completely different hole in the end. And one thing that I always take as for granted with the planet I have been observing is that the star is an A star that is fast rotating. So all the possible lines that you could see due to absorption on the star are so wide, they're completely widespread, I can just ignore them, which sounds terrible to say in that way. But yeah, I'm one of those people that tries to ignore the star as much as possible. But actually, yes, we have to learn from these space missions that we're doing also in our solar system. And we definitely also have to account for possible variabilities of stars. As we continue in this field, we have to open our minds and get stellar people in trying to help us understand what we're doing. We're quite a young field. So exoplanet atmospheres is only really a thing. I don't even know when it started, maybe like 2000, 2001, sort of with the first transiting planet.
Decades-ish, yeah.
Yes, so we're really young. And this means in the end that we have to take all the influences from all the other fields and try to learn. I always say, let's not try to reinvent the wheel, but we can maybe also learn something from, I don't know, galaxy formation. Maybe we can get people with their knowledge or star evolution in order to better understand what we are actually looking at. It's not only learning from spacecraft, but it's also learning from interdisciplinary fields.
Yeah. Absolutely. And I mean, especially with this transit method that we were describing, which is like the bread and butter of atmosphere, exoplanetary atmosphere stuff. It's the 101. But the whole point with the transit is that you're looking at the starlight passing through the atmosphere, or in the case of emissions, lighting up the atmosphere. So you can't just say that you don't care what the starlight is doing, because the starlight from a really hot star and a really cold star are two very different types. And it's like, we said that basically you see these absorptions, and then you're figuring out what it was that subtracted. And then if you don't know what the thing is in the first place, then that's not going to help you. And some of these colder stars, okay, Bibiana's talking about O and A stars. I don't want to even think about them. I'm more of a cold star girl. But these cooler stars, some of the molecules that we can expect to find in some of these exoplanetary atmospheres, you can find on the surface of these stars. And like we said, some of these hot Jupiters have similar temperatures as some of these colder stars. So
you count one and one together, right?
Well,
you're looking at
exactly. Surely that might be here's a problem for you. What happens if an ultra hot Jupiter, which must be pretty bright in itself, right? What happens if that's got a large Titan-esque moon that's going around it as well? Surely that's another little bit of noise that you can have in your data.
We absolutely.
Listeners can't see it, but me and Bibiana are both laughing.
So at this conference in Las Vegas, they did not only talk about stars, they also talked about exomoons. And it's definitely also a field that is sort of starting to get there. So people are like, oh, planets are boring. Let's not look at exoplanets anymore. Let's go for their moons. And you're like, but we don't even understand the planet. Let's not even talk about the star, right? So yeah, it is definitely also a thing. So
you know when you're procrastinating and you're like, you really need to do something, but it's really boring. So you end up doing the other thing that you also don't need to do. But you're like, well,
exomoons are what people do when they should be doing ultra hot Jupiters. And ultra hot Jupiters are what people do if they should be.
What stellar astronomer should be doing.
Ouch! We got
okay.
We almost got hung up on this.
Apologize.
Oh no!
I really have to apologize to all the people who are interested in exomoons. Now we actually
I'm kidding.
I actually met the guy in Vegas that is working on exomoons. I shouldn't be mean to him. So
no.
I'm really sorry.
It's sibling rivalry.
That's very.
We all make fun of each other's field.
We're competing to get time. So
I've just had a thought about exo hot Jupiters, ultra hot Jupiters.
Oh God!
How long do they last? Because presumably, do they?
Great question.
Do they get blown away? Because obviously, if it's all atmosphere and they're that close to a raging star that's got a nice good solar wind going, stellar wind.
I mean, some of the planets are actually some of the planets are actually losing their atmospheres in the sense of, literally the star blowing away their atmosphere. So that's also something we can observe. So one thing that we always say is that these atmospheres are hydrogen and helium dominated. So the only two non-metals that we know, right? But
non-metals.
Non-metals. And they are then sort of being observed as atmospheric escape. So there is actually stuff happening with like blowing away these atmospheres. But in the terms of lifetime, I must admit, I'm absolutely not an expert on how long these ultra Jupiters would be in their place.
Anyone is.
But I mean,
probably not. No.
Something like those types of supernova where one star's stripping the atmosphere off another star. Can something like that happen with an ultra hot Jupiter? Could the host star be actually not just blowing it away, but actually stripping it away gravitationally and actually, well,
we do get trails, right? Did I dream that? I feel like I've read about sort of exoplanetary atmosphere trails where the atmosphere
literally is pouring down the gravity well of the host star.
Yeah.
Yes, absolutely. If I'm not completely mistaken, and I'm very sorry to my supervisor if I am, I think the planet he has been observing, Kelt 9, which is this like super hot planet that I have been talking about, that is like 4,500 Kelvin that we talked about in the beginning. That one, if I remember correctly, is losing its atmosphere to its host star in some sort of way. But I'm not entirely sure in what sense that is sort of something we can really observe, because I think the time scales are so much longer than we could ever imagine.
Well, again, this is where modeling comes in. in astronomy. You want to see what happens across 50 million years? Zoop, just speed it up.
Just speed it up and hope it doesn't crash.
Exactly, which it will do. 500.
No, and if you're a betting person, is it possible, if in a planetary system that has an ultra hot Jupiter, could you also have a nice rocky planet in the Goldilocks zone?
Absolutely. I would say the cool thing with ultra Jupiters is that we don't know anything about, or we do know some things, but we don't know properly how they form, how they migrate. And I was always like, but if you have an ultra Jupiter that was formed outside where it's super cold and then it moved inwards, it must have like destroyed everything on its way, right? They must have kicked out every other planet that was possibly in there. But that's not even the case. There are really some ultra Jupiters that have like even something inside, like in a closer in orbit or just outside. So I'm pretty sure that doesn't matter in the end. And these planetary systems are then more in a so-called resonance. So they have like cool resonance chain in the way that they are orbiting. I mean, because there's just so much going on.
It'd be super cool, wouldn't it? If you were a conscious, if you were a spacefaring alien civilization watching your hot Jupiter go round your ultra hot Jupiter go round your host star, there'd be something.
As you do.
Presumably, that would look pretty cool as a
I think
in
so.
the night
It would
sky.
probably be even more impressive than looking at Venus transiting, right? So it'd probably be bigger going in front.
This is something me and Bibiana spoke about the other day, as you do when you're just talking about #JustGirl things, talking about planetary atmospheres. About this thing that I think it's an ongoing research question, because I haven't seen a sorry, let me start that again. I think it's an ongoing research question because I don't remember ever seeing a sort of textbook, this is the case answer about, do all hot Jupiters form far away and then migrate inwards, or can they actually form closer to their host star? Because one of the things, we talked about how hot Jupiters is something that doesn't exist in our solar system. And in our solar system, historically, for a long time, we were like, okay, well, you have rocky planets and you have gas planets. And rocky planets must be the ones that form close to the star, because that's where sort of rocks and metals can survive. And then only further out is it cold enough for ice crystals and stuff like that to condense and form gas and ice planets, right? And the cool thing about exoplanets, the whole reason I would say to look at exoplanets is to see other versions of solar systems, to get a broader understanding of how planet formation more generally can work. And so with hot Jupiters, they really threw a wrench in the works for like our tidy little thing of rocky planets are close in and gas planets are far out. And then it's like, no. And the question being then, how do these form, and how do they survive whatever formation processes and moving around and all this stuff? And I remember we did an episode about solar system formation, and we talked about how it's so hard to rewind the clock and to figure out like what actually happened. You can't CSI your way out of this one.
Well, no, it's back to my washing machine, isn't it? You take the clothes out at the end of the cycle. It's like, how did I put them back in? Surely I can rewind the whole thing and work out what order I put.
Figure out which
one.
Did
I put my pink socks in before my white shirt? I don't know.
Yeah, and when did I ruin this wash?
At what point? Yeah,
at one point in time, yeah.
Some questions are better left unanswered.
Though on the other hand, yes, pink sock in white laundry sounds absolutely terrible. But on the other hand, I think figuring out how these ultra-hot Jupiters form and probably migrate from outwards inwards, I think that's one of these standing questions, and I would love to see an answer. And this is sort of where atmospheres and formation need to sort of go in hand, because of course, depending on where you formed and where you sort of got your atmosphere as a gas giant will change your composition of your atmosphere.
Yeah.
So it's not only that we say, okay, so you have formed, I don't know how far away from the planet, and this is how you got your atmosphere, and that's it. But this atmosphere is probably very much subject to change as it moves inwards in the disk, for example. So I guess observations of atmospheres will not only tell you about, hey, what is in this atmosphere status now, but what are possible scenarios to actually get there?
Absolutely.
And how did this effect occur given your formation location?
This is why I love protoplanetary disks so much, and looking at the sort of planet formation, what kind of childhood trauma in the early stages of the planet's formation resulted in whatever complex emotional issues that the fully formed adult planets have, and looking at these sort of pubescent planets in the sort of stage in between, because the protoplanetary disk is like the soil from which the flowering planets grow, right? And so looking at what is happening in the disk, what kind of chemistry is going on, what kind of like accretion processes are going on, all of these things are going to have an impact on the planets that are formed later on. So I think it's really cool that we're getting some really, really great cutting edge observations of protoplanetary disks now. That's another very young field, actually. And the sort of resolution of which we're getting, like the ALMA observations of the protoplanetary disks, are divine. I love them.
That is also the very scary part about them, right? What are they going to tell us in the end? Are they going to tell us those planets should actually not exist?
Oh no, please don't.
How did that work? No, so for me, protoplanetary disks have always been like a very scary subject. So whenever someone, I know you love them with
I know
all of your body. For me, really, protoplanetary disks are,
It's like you don't want to know.
The hard one.
Don't tell me.
I really want to know. I really want to know everything about them, and I really want to understand how those disks that we observe actually result in a planet. Because for me, this is just mind blowing that something that is orbiting around the forming star is just producing planets, and then all of a sudden this planet decides, I don't like it here anymore, and migrates inwards.
I'm leaving.
Yeah, something like that. I'm leaving.
The emotional teenager planets. Yeah, exactly.
Exactly. So if you compare it to sort of the life cycle of a human being, and compare it to being a kid and then going through your puberty and then becoming an
it's
adult.
The complicated traumas in early childhood that result in migration, right? We could write a whole thing about that.
I mean, it may have migrated in, migrated back out, and migrated back in again. Surely, it could be all sorts.
Sometimes it patches things up.
Yeah, it's like leaves home.
You know what, Mom? You were right. It was a phase.
Didn't like it there. No. Was too warm.
No, but it is super interesting, and I think it is super interesting. And looking at the sort of timescales that planets form, it's actually quite fast, but of course not fast enough that we can watch it. Like I said, models are very useful because then you can sort of try to figure out in sort of 60 seconds what a 10 million year process might look like. Mm-hmm. But this is the thing with both protoplanetary disks and sort of ranging from young exoplanets to older exoplanets. All you're doing is looking at one system in a snapshot of time, and you're looking at it today. What does it look like now? And then you can look at the star and say, okay, well, this star is 1 million years old, or it's 10 million years old. And then you get a feel for how old then the system might be as a whole. And but you can't really like draw a linear relationship like, okay, well, this system started out this way, then it did this, and then it did this. Like, we're just sort of triangulated by looking at a bunch of different systems at different ages, and then seeing what young systems and older systems have in common to figure out, well, this might be then a feature of the young part or the part that it's old, So it's very difficult in astronomy in general, and this is the same for galaxies and whatever else. Because things happen on such enormous timescales, you can't just pick one and follow it, like researchers do with fruit flies or whatever. You sort of just have to look at every kind of system and then sort of try to figure out how things scale with age and with time.
In the end, you want a catch-all solution, right? You want to be able to run your model and be able, given these parameters that you put in the beginning, you want to be able to reproduce every possible observation that we have. Yeah. And sadly, but also on a really good side, is that we're not capable of doing that. So meaning we still have our jobs, we still have time to figure it out.
Another paycheck.
Another paycheck coming in. No, I think our curiosity is sort of fed by that, right? That we still don't know how they form. We don't know how they gain their atmospheres. We don't know how they even become those planets that they are in the first
place. Do they lose their atmospheres?
Do they lose? They probably do at some point, but how exactly? So I think this remaining question, yes, it will probably not bring peace on Earth. That is not going to happen, but it's at least going to trigger people's interests in science. It's going to sort of help people relate to what we're doing on a daily basis. When you tell them, we don't even know how our solar system forms, because there are so many groups out there that are not agreeing on any solution. So how are we going to figure out what happened light years away?
And the wonderful thing is that every time in science that you open one door, you're not actually just opening the door to an answer. You're just opening to another corridor with 25,000 more doors. I
was going to say, one day you'll get an email from an AI that will say, "Yeah, I've cracked it. I've got the model. It explains everything." How?
Become a painter.
Well, I mean,
please don't.
How far away do you think that? How far away do you think that day is? Are we in the very early stages of this kind of quest, or are we in the closing stages of a quest?
I think we're in the Renaissance, right? This is like we've just kind of recently, and I say 21st century, made the breakthrough of actually having the computing powers in our technology to do big things. And I think that sort of the year 2000 to the year 2100 or something will probably be a sort of Renaissance golden age, right? I don't know. Sorry, I hijacked the question.
I heard something just about the computing power. I heard something when I was a kid. The Cray supercomputer came out, and it was something like 1 billion calculations a second. And recently, the new Cray has come out, and it's 1 billion calculations. It's 1 billion times faster. So,
that's nuts. It's and you're only 14 years old.
Exactly, and this is well, no, from the 80s to now is it's 1 billion times faster. So, if they carry that kind of speed increase up, then who knows what kind of...
But it's not only that, right? It's not just doing the calculations, it's also how are we going to handle this data that is coming in. I see myself struggling sometimes, taking observations from, I don't know, the very large telescope in Chile with espresso. And I'm like, that takes a lot of time to actually look at this data because it's just so much. And then I think of, okay, what am I going to do when James Webb data is going to come in?
Yeah. We're hire more postdocs.
We're going to be screwed.
That's my supervisor.
Well, that's why you need to encourage more people to do astronomy so that they can help you with the data, right?
Absolutely. That's my favorite. That's always my go-to answer, in a sort of outreach capacity when kids ask a question that there is no answer to, questions like what shape is the universe or what's inside a black hole or something like that. I'm always like, well, when you find out, call me and we will split the Nobel Prize sum 50-50. Right? Can we agree on that now? And I've said this probably to 25 plus kids. So statistically, one day
it might happen.
Every time I say that, the chances go up by
let's try and enthuse a listener who was umming and ahhing about doing their masters in astronomy.
Do it.
Well, do it. What's the most exciting thing you found out so far about ultra hot Jupiters? What's the poster child? What's the poster thing? What's the headline of ultra hot Jupiters?
Oh wow, I'm not going to sell this very well. Let me think about that for a second, because I would say that I don't know anything about them, but that is not going to help people deciding to go into.
I've been studying it for years. So I know nothing.
Tagline: I don't know anything.
Yeah. No, I think for me, the most exciting part about ultra Jupiters is that, yes, we don't have anything close to them in our own solar system. Yes, we have no idea about how they formed. Yes, there are so many open questions, but still we are able to look at something that is so far away by just staring at it for a night. For me, the most crazy thing that happened is when I started my PhD and my supervisor was like, you're not going to use my code, you're going to write your own, and you tell me when you detected iron on this planet because I know it's in there. And I was just sitting there, nothing worked out. I was sitting at my code trying to figure out why it wouldn't compile or run through. And I was like, okay, this is never going to happen. And by the moment I showed him the plot of my iron detection, which was the completely wrong velocity because I had done some plus minus sign wrong somewhere. But when I showed him I detected iron on a planet, for me, wow. I just figured, wow, that's so weird. How does that even work? And then I tried to figure out what is actually wrong with this planet. There is iron on it. It sort of hit me in that moment. I was like, okay, I'm looking at a planet super far away and it has iron on it. What?
I mean, I think that is one of the most exciting things possible, is that you're the first person to observe it. You're the first. You are the. I mean, I always think what a magical moment it must have been for Galileo to kind of first see things through a telescope. And it's just like, I'm the first person in all of history to ever have seen this. Or Hooke looking at bacteria and I'm the first person. So
if you're listening to this and you're considering a career in science, I actually do think completely serious. I know I joke a lot on the show, but I think that one of the most amazing things is exactly this feeling. You know, we get really bogged down in the sort of day-to-day mundane. It's Tuesday at 10 a.m. and your code's not compiling and you're like, oh, I hate this. And you get so mad at this tiny little thing. But when you take a step back, and the fact that as scientist, you get to walk around and when people ask you what you do, you're like, I detect molecules on planets light years and light years away. Like, it's such a humbling and frankly just really cool thing to be doing with your life. Like, you have one life. What do you want to dedicate it to? Arts, science, whatever.
And I'm assuming that it's quite likely in the coming decades that one person might be the person that is the first person to detect like unambiguous sign of extraterrestrial life.
Yeah, and my money's on Bibiana.
Wow.
Just saying.
on an ultra-hot Jupiter.
I'm really sorry. I don't think so. Yeah. But Matthew, going back to what you said, do you really think that Galileo was there and was like, oh, I was the first one? I don't think you could have asked him that question in the sense of like, what is sort of your contribution? What would you be standing there and saying, yeah, I was the first one to detect that? I think it's for the future people to sort of tell what we did, what was crazy good about us, or what was sort of the best thing. And yes, you're trying to sort of extrapolate it and tell people you should go into science because I am able to detect this. And yes, I was not the first to detect iron on this planet because I know my supervisor detected this iron on this planet before. Not really 2 weeks before. He actually published in Nature before with this detection. So I was like, okay. I was not the first one, but for me,
also found iron.
Absolutely. For me, it was the first.
And science is very collaborative in this way. This is something that I think the sort of image of the old white bearded guy mumbling in the basement is it's so outdated, and I think a lot of people fortunately know this now. But science is a very collaborative thing. It's very seldom, at least in astronomy. It's different. I think like different branches of science maybe have more solo teams or solo groups of just one or two people that do publications. But at least in astronomy, if you look at astronomy papers, there's nearly always like 5+ authors on a paper, because there's so many components to going from say an observation and then going through the modeling and then going through the calibration with the telescope and then actually making some kind of interpretation and then testing that and all this. There are so many steps. Especially, I would say that astronomy is one of the more collaborative fields, which I think is a plus. I love the fact that
I think
we all work together.
Anything that becomes extremely complicated and like just to be an expert, you have to be hyper specialized.
Yes.
It's such a mature science, isn't it? We said Galileo.
Yeah.
It's been around since way before then. The Babylonians or whatever.
Yeah. Who was the first data scientist? That's
it's ridiculous. So it's been around a long time, hasn't it? So you've got this really mature and absolutely that kind of diversity and everything else is so important because because it's complicated and you need that kind of diversity of thought to come even close to answers. Yeah.
I think that puts it very nicely. I was in a Einstein museum just a few days back, and I was just there like, this is not happening anymore nowadays. That if you think of these big names that you have in physics, I don't know, going from Einstein, and then you go, I don't know, Lawrence, then you go, I don't know, there are so many names, I cannot even tell you all of them. But if you sort of go through all these names, this is not happening anymore. So we are all in this together, so to say, to quote High School Musical on this show as well. We're all in this together, we take it hand by hand, and it's not that I am detecting something for the first time, but it's the people that I have collaborated with that are detecting something for the first time. I mean, we are 24 authors on my very first paper. Just bringing the point across where you said 5+. Yes, I have 24 authors.
That's minimum. Yeah. You can easily get 50. Like,
yeah, I mean, just to roll back on my Galileo, I wasn't meaning that he wasn't humble. But I more meant that the actual discovery, whether it's you or a team or whatever, it's still it's still the fact that you're furthering the knowledge of humankind, isn't it? And yes, obviously you'll have people in the future looking back and deciding whether it was important or not. But
but absolutely, you're right. You are right though that it is, the feeling of, oh my God, I'm part of a discovery. This is not diluted by having numerous collaborators. You still have that feeling. If it's just you or if you're a team of 24, the feeling is very valid and very, very rewarding, and very, very excellent for students considering careers in astronomy. So it's a very I'm going to say humbling again. It's the best word I can think of. Is there any better reminder of how tiny insignificant we are? Which, actually, I don't really stand by. People often talk about this, like, when you look at astronomy and don't you think about how tiny and insignificant we are and stuff like that. But I actually feel like the opposite, because do you know who doesn't have thoughts and dreams and feelings and love? Stars. They're just big old hydrogen things.
You don't know that.
I'm more special. I'm more complicated.
The panpsychic might disagree with you, but it's a little bit of a fringe. It's a fringe theory.
I'll let them. Yeah, but humans. I think human life and humans as individuals are so wonderful and complicated and everything. And I think rather than looking at all the different stars and planets and being like, wow, I'm so tiny, it's more like, wow, I'm so tiny and I'm kicking ass at
I'm still
figuring
getting it.
this stuff out.
Yeah. I mean, there is that.
I'm cool.
There is that frightening thought, isn't it? That we might actually be the only creature in the universe that that has begun to understand the universe.
Yeah.
And that's frightening.
Idiots.
But yeah, that's quite frightening.
We're so stupid. That's the worst part. Have you seen politics lately?
I know, yeah, it's crazy.
I think on a closing note, we can talk about how it's so cool that, linking it as well to discoveries and all these sort of like philosophy of science things, that it's so cool that something like ultra-hot Jupiters, because exoplanetary science is so young, we did not even really think about or consider the possibility of them existing, even just like within our lifetimes ago,
I absolutely agree. The day I met Didier Queloz, and I was just like, oh, you were the guy that detected the first exoplanet around the solar-like star using the radial velocity method. And he was like, yes, nope. I am. And I remember it was like, I'm not even sure. I think it was just before he got his Nobel Prize for it. And he was in Zurich. And I was just there like, oh my gosh, I just met the person that paper we're always citing. He was like, wow, I feel so important right now. And then I'm just thinking, yeah, well, it took quite a long time until he got his Nobel Prize for that. So, I mean, they discovered it in 1995 and they got their Nobel Prize in 2019. So it took quite some time to sort of realize that this is a major discovery. So I feel like even if we're doing this collaboratively, even if ultra Jupiters are probably not the targets that we want to live on at all, I feel like pulling all together in direction of trying to understand the universe, trying to understand how these planets form, will bring us further together.
Yeah, well, I mean, you never know where understanding will take you anyway, do you? I mean, that's what I like about research.
Define understanding, right?
No, absolutely. It's such a young field, and we don't know that much, but I do think we can say with confidence that there's a lot of understanding coming our way over the next just few years. of course, decades and centuries, but even just in within the next decade, I think for sure. Some very exciting things happening.
Well, thanks very much for joining us. This has been an awesome chat. I'm trying to think about all the craziness that would be happening trying to live on an ultra hot Jupiter right now.
Don't try. Thank you very much for having me.
Bibiana, it's been super great to have you here. Thank you so much for joining us and teaching us all about our favorite. Now you can really impress your friends when they inevitably ask you, as kids do these days, what is your favorite type of exoplanet? And you can say, actually, my favorite is an ultra hot Jupiter.
What's your favorite ultra hot Jupiter?
Oh, for me, that definitely was 189b, which, by the way, my mom asked me, why would you call a planet like that? And I was like, Mom, it was not me, sadly. She was like, can't you just call it BB1? I was like, I'm going to consider that next time. So sadly, the name is not really catchy, but for me, that's my absolute favorite planet because it was the planet that I worked on first in my PhD, where we discovered titanium oxide, where we found sort of weird things happening in the atmosphere. And for me, that was just mind-blowing to see.
I will send an email to the Exoplanet Archive and ask them formally to rename it to Bibiana's mom's planet, because I think that's super cute.
The Interplanetary podcast is alive!
There we go, Linn. Thanks very much for organising that. That was an awesome interview. I'd never heard of ultra hot Jupiters before. I'd heard of hot Jupiters, but never ultra hot Jupiters.
You know what? Me neither until quite recently. It was when I started my PhD that I started hearing about this. But it's kind of a new-ish term, I think. I mean, exoplanet science as a whole is so young compared to basically any other part of astronomy. I mean, most of astronomy, if people have been looking at stars for a very long time, but people have not been looking at exoplanets in details for long at all. So we're still taking submissions for ideas about fun names and things like that.
I guess it's like the classification of things is a bit like evolution, isn't it? And the classification of animals. Yeah. You're just going to get an explosion of classification of exoplanets as we discover them, just like we did fossils and things like that. And now that's another episode idea, talking about classification of things in space, because that's a whole deep dive. Even classifying what a planet is very contentious. Poor Pluto, for example. I had a talk with actually my old school that I went to. I had a little talk with the year 8 class, and I was answering some questions about space. And we got to talking about why Pluto is not a planet. I'm so sorry, but I completely agree. It's not a planet. Come on, the moon is bigger than Pluto. How can Pluto be a planet? Gotta be consistent, guys. I think the big one is it hasn't cleared its orbit.
That's the one.
I think you're allowed to have Trojans, but you're not allowed to have you're not allowed
Trojans.
Yeah, you're allowed Trojans. But in your Lagrange points. Yes. But you're not allowed to be in a kind of great big asteroid field full of similar sized objects. That's ridiculous.
You must be this big to ride this solar system.
If there was a big old planet in the Kuiper belt that had mopped up all your Plutos and your Vestas, then that would have been a planet.
Well done, girl. You are definitely a planet. Hell
you are definitely a planet.
Congratulations.
So, well done.
You have moved on to the next round.
You moved on.
And then she battles Jupiter.
Yeah,
well,
maybe Jupiter battles Brown Dwarf.
Exactly.
Then Brown Dwarf battles Sun.
Yeah. We just
and it
keep
just
going.
Goes up like that and just
up
keeps
and up
going
and up until you have entire galaxies battling.
Until it's black holes, supermassive black holes.
Oh my god, I would watch that. Is someone taking notes? We need the sci-fi to exist.
I need to thank the rest of the patrons, but actually, I did want to mention one thing. Because there's one mission that I know that the patrons are excited about, and that's the Psyche mission, which is talking of planetesimals. I guess that the Psyche mission is to an asteroid that looks like it's a protoplanet that had its outside smashed off and just left this iron core, and NASA are sending a probe to it, but it's been delayed. It's not going to launch this year anymore because they just can't get it ready in time. So,
oh no, what? That's never happened before. A delay?
No, that never happened. A delay? Can you believe
how
such
unforeseen? Yeah, no, I'm obsessed with this mission. I'm super excited about it. I'm not going to get my hopes up about launch dates anytime soon, but it's really, really cool.
It's going to be really cool. I really hope that the pictures are going to be as spectacular as I hope they're going to be.
I hope so.
I hope so, particularly because there's lots of artist impressions that are really good.
Yeah, they're setting the bar too high. I feel like they should like cut back a little bit, go back to the crayons maybe, and then people will be really, really excited. I'm also very excited about July 12th is when we're going to get the first real images from James Webb.
Oh my God.
Well, I heard a little bird in the shape of a NASA administrator on some kind of panel, I can't remember who it was, did say that apparently one of the first pictures we're going to get will be an extragalactic deep field, kind of like the Hubble one, that's going to really show off the telescope's abilities. So I'm very, I mean, I don't even work in for me, if it's like more than sort of 100 light years away, I'm kind of not interested because so I mean, I don't really do outside of our galaxy stuff, but even I'm very excited about that. I think that's a great way to
would you like
it.
Would you like it if it managed to get an image of Proxima C? Would that be good? Or maybe
that would be fine, I guess. I'm saying this like while dribbling kind of thing and foaming at the mouth. Yes, I would. I guess I would be fine with that. I guess that would be kind of cool. Okay, whatever.
Right, that would be cool,
sweating.
Or the TRAPPIST system or something like that. Managed to get some
all of the above
spectroscopy of some TRAPPIST planet. That'd be quite good, wouldn't it?
I guess I would be okay with that.
Okay, good. Good.
If anyone wants to send me some James Webb data for this. Although we are actually getting a lot of exoplanet data from James Webb. So there's a lot of telescope time allocated to exoplanet stuff, which I think is really cool. I think it's very nice that we're getting so much attention from the community.
Surely, yes. I feel as though that's why it was built, for exoplanets. I feel as though that's surely.
I mean, in my heart, yes.
Yeah.
I don't know. When did they start planning it? 96 or something like that?
Yeah. Well, it's just when exoplanets were just starting to be cool then.
Just about, yeah.
Unlike the ultra hot Jupiters, which are just starting to get hot.
Hot, and ever more hotter.
Right. Well, I know one person that's going to be upset by the delay in Psyche, and that's Bob Hodges. I know that's his favourite mission. So sorry about that, Bob. Bob's one of the patrons, as is Alden Vala, Ben Guthrie, Bob Moore, Gene Watchtanik, Jacob Economy, Jim King, Kenton Hokanson, Mark Huber, Mark Kelly, Mark Schoen, Marissa Davis, Malta Keisling, Neil Hansen, Niklas Gillenstein, Paul Hilton, Rob Annable, Ronald Hatcher, Seth Haberline, Steve Croucher, Tristram Tupperhide, Tyrrell McAllister. But there we go.
Excellent.
Lynn, what have you got coming up other than pictures from James Webb? Anything fancy?
Anything fancy? Well, fancy. Yeah, I've got a very crazy summer in front of me, actually. I'm going away to conferences and presenting some of my work, which is very exciting. And at least we're all making the assumption that COVID has now gone away forever. So I guess it's back to in-person conferences, and we'll see if I get sick. But it's very, very exciting. I mean, there's a lot coming up with Cryo-RS Plus, the telescope that I'm working with. And maybe I'm going to jinx it now by saying it, but I might even be going to Paranal at some point in the next year to go to the telescope to use it.
Oh, yes. Now tell me you're going to interview someone when you get there.
I had not thought of that, but now that you've said it, of course I'm going to do that. That's a genius idea.
Yeah, more than I am a genius.
That is true. That is true.
Rightly point out.
Rightly so. Yeah. What about yourself? So we already covered that.
I've got enough excitement for 1 year, and that's going to see them. Yeah. Hopefully, fingers crossed, the maiden launch of Vega. We'll see. It's going to be absolutely brilliant. It's the best of all the rockets in terms of how quickly it gets off the launch pad.
It is like a bottle rocket.
It is a proper
Mentos and Coke.
Yeah, exactly.
That's what's in there.
It's out of there. It's not It's not like Saturn V that sort of hangs around at the launch pad for about half a day, going,
like
I'm just about to get on.
Like a bored teenager. Yeah.
I'm going to climb out of Earth's gravity well, I promise.
Yeah. You keep going, baby. You can do it.
You keep. Oh, yes, you've just done it.
Yeah.
Right, that's it. I'm going to say goodbye to the Spodcats now.
Say goodbye. Bye, everyone.
Bye.
Bye.